All right, hello everyone. I'm going to talk about computer research, and I would like to get the group on to that analysis and implementation session. In the session, we have 4 talks lined up. With that, I would like to invite the first speaker, Titzer. So with that,
Thank you. Thanks for the opportunity to present our work here. ASPLOS is actually my first ASPLOS, and it's my first ASPLOS paper. So this is joint work with Heather Miller and our students who are listed here. So the motivation, as I said in my lightning talk, is that programs have bugs and sometimes run slow. And so for the first thing, for having bugs, there are a few static analysis techniques that we can apply, like type checking, linting, and verification. But there are many more dynamic analysis techniques that we can apply, such as tracing, sanitizers, leak detectors, race detectors, and so on. And for the last part, we definitely need dynamic tools. So we need profiling and coverage, memory analysis, cache simulators, and so on. So this paper is all about dynamic analysis for WebAssembly code. It's all built on our research engine called Wizard. It's a fast WASM engine. It's designed specifically for doing research, so it's not a product VM. The insights that we had from our paper is that most dynamic analyses are actually tied to specific locations in the program. So our instrumentation technique is going to exploit that fact. They're often very sparse in time and space. But other than that, they're very extremely varied in logic. And so we need a programmable mechanism here. I give a few examples here: code coverage, branch profiling, memory profiling, dynamic call graphic construction. On the debugging side, watch points, breakpoints, and tracing, so on. And the idea is that we're going to use one mechanism to do all of these, which is basically callbacks. But that's not what we call them in Wizard. We call them probes. And the idea is that Wizard is one of the few WebAssembly engines that has an interpreter. Most of them are compiled. And having an interpreter makes it easy to have a callback API for probes. So if we have some WebAssembly code here shown disassembled, but obviously it's a binary format, there's an execution point, and you can get a callback where you are told to function the PC, and the user callback can look into the state of the program through an API called a frame accessor. So the easiest way to do this is you have a callback for every single bytecode that's executed. This is useful for tracing modes and so on. There's an efficient technique that we use here called dispatch table switching. So in the interpreter, there's a data structure, which is effectively the logic to do for every bytecode. Normally, when instrumentation is not on, that points directly to handlers. When we turn instrumentation on, it's a separate table that actually points to one that does have instrumentation. And you can switch back and forth. And so there's no overhead when you're not running with instrumentation. But of course, every bytecode is maybe a bit too heavyweight, so we can have pointed instrumentation. So in particular, we call these local probes. So you can insert a callback on a particular point of interest in the code. And when that executes, you will get a callback. That's implemented with bytecode overwriting. So the actual byte there that the interpreter is going to load is going to be overwritten with something illegal. And then we can call the user callback. And this is so that we don't have overhead when this for the other instructions that are not probed. And then we can get to the original code, but because we've made a copy, and so all the offsets match up and stuff like that. And so then we can do the original logic. We can also remove the probe easily because we can just copy this byte over. So this removing the instrumentation is the superpower of doing it this way. So I'll give you an example of how we build a complex analysis like code coverage. So you should think of probes as the building blocks for other analyses, in particular, code coverage. So if we were to implement code coverage at a basic block granularity, we can insert probes at the beginning of every basic block. When they fire, they call into a callback that actually keeps some state on the side and just tracks which basic blocks have been executed. And then because we can remove them, we can remove the probe because we only need to record that block has been executed once. And so as the program executes, it magically removes its overhead by removing the instrumentation, and eventually we get to the point where all the paths that have executed have removed their instrumentation, and the hot code, which repeatedly executes, doesn't have any overhead. So you asymptotically approach the performance that you would have without instrumentation. So with this mechanism, you can implement many analyses, and so many standard analyses come out of the box. They're all implemented with the same mechanism, so the engine and all the execution tiers only know about probes. They don't know about these things. So these things include Loupe profiling, branch profiling, code coverage, instruction tracing, call graph construction, function profiling, and many things like that, including a debugger REPL. So if you were to measure the overhead of this, so this is actual performance data. If you were to implement branch profiling using bytecode rewriting, so actually intrusively modifying the WASM code by injecting instrumentation versus doing a local probe in Wizard's interpreter, the blue is less overhead, so it's around the order of 15% to 20% versus 2x with a bytecode rewriting. But this is an interpreter. And so does it really have competitive performance? Does it really have an overhead that's comparable to what you would want to run? And the answer is, well, this is distorted because we're running an interpreter, which is slow. It's a slow baseline. It could be 5 to 30 times slower than JIT compiled code. So this is data from the JIT compiler, comparing the performance of JIT code versus an interpreter. So we need to do this in a way that actually works well in the JIT scenario as well. So this is not a transferable result in terms of overhead. So we built a baseline compiler for Wizard, published a paper about that this year. And the idea is that it's a state-of-the-art single-pass compiler, and it's designed to be very simple and generate code very quickly, and it supports local probes. So as the program analyzer, you don't know that the JIT exists. And so most of the paper's meat is actually about making this work in the JIT compiler in a completely transparent way. One of the tricks here is to use the same stack frame layout as the interpreter so that you can switch between execution tiers easily. I'm not going to explain all the details of that there, but the idea is that basically, because we can switch between the interpreter and JIT and back, when we add instrumentation, we can switch back to the interpreter if necessary. Normally, we're going to tier up to the JIT compiler when hot functions and hot loops are detected, and it won't tier down because it doesn't do speculative optimizations. But inserting new instrumentation is effectively invalidating compiled code, and so it will switch back to the interpreter if new probes have been inserted. So just an illustration of that. So baseline compilation is effectively an abstract interpreter that emits machine code, one instruction at a time. It produces remarkably good code because of the structure of WebAssembly. If we have a probe in the code, it's going to show up as one of these ugly purple colors here. It's very easy for the JIT to see that that's where it needs to insert a call to instrumentation. One of the observations that we have is that there's many instrumentation tasks that have low overhead things that they want to collect. For example, just counters. And so the JIT compiler recognizes special kinds of probes, such as counters, and will emit intrinsified code. So a counter might just be 2 inline instructions, which is obviously less overhead than calling into a runtime to do that. Other types of probes can also be intrinsified too. For example, the branch profiler needs to have the top of stack value, which determines the direction of the branch, and we compile that specially so we just pass that top of stack value as opposed to reifying effectively a mirror, which is the what you can see the program state through. One of the important things about instrumentation and dynamic instrumentation is consistency. In particular, what happens if you insert a probe and then remove a probe? When do those take effect? And what is the firing order for probes? So if you're running multiple different programming analyses, maybe you want to make sure that they don't step on each other. And so we define some consistency properties, in particular, frame modification consistency. So it is effectively like an interpreter is running your code. If you modify the frame, you go directly back to the interpreter. And that's really important because otherwise analyses will get confused or they will stomp on each other's toes. So again, those are insertion and firing order, frame modification consistency, and effectively it feels like there's just an interpreter in there. And so a lot of work behind the scenes happens to make sure that that kind of just seems like that. So the way that's supported is through de-optimization, which is a known technique for dealing with speculative optimizations. Bytecode is a source of truth for instrumentation. So imagine if we've compiled this code that had one probe at the beginning, we might have inserted some counter code here. If we then insert a probe later, this machine code, even though it's going to execute the WASM program correctly, it doesn't have the instrumentation, so we de-optimize it. So that means that all the frames are rewritten so they'll go back to the interpreter and we throw away that machine code. And if that code is still hot, we can just warm up again and it will be JIT compiled again. Some performance results here. So I don't have time to go through all of them, but this is a graph of basically 2 different instrumentation workloads. On the left, this is the hotness monitor, which is one of my favorite names for a monitor. It basically counts the frequency of every instruction in the program. So this is heavyweight. So there's a counter for every single instruction in the program. And so this is a log plot. You can see that some of the benchmarks have up to 100x overhead. because without JIT intrinsification and optimizing that probe overhead, it's literally a runtime call for every instruction. So when we implement the optimization in the JIT compiler, it basically reduces that overhead by a factor of 10. So we have a hotness monitor that maybe is only 10 times slower than the original code. The right graph is for the branch monitor. That is basically every branch is instrumented and it will record the direction of every branch. And we see the overheads are overall smaller because there's fewer branch instructions than so maybe 1 in 5. And basically the overhead goes from a factor of 10 to about a factor of 2. And again, this is in JIT code. So this means that you can have a branch monitor that records all the control flow data and has about a 2x overhead on execution time. And so that breaks down, we further drill into why those overheads go down by so much, and you can attribute it to those different things, in particular, the time spent in the dispatch logic. So when you're in the JIT code, you have to then figure out what probe to call. So there's some logic in the runtime, and there's also the overhead of the actual probe itself. And so the various different colored bars here are the overheads and how much is removed by JIT intrinsification. So that is about it that I've got for the presentation. Thanks for your time, and I'm happy to answer questions.
So I have a question. So I noticed that they are instrumenting function exit and graph detection. But can you, like, if I want to analyze memory instructions or just arithmetic integers, can you do that?
Yes, so we do have a monitor that does instrument all memory accesses. WebAssembly effectively has one big large memory, so you don't know what alias is what, so it's harder to make it like targeted. So local probes, you can effectively instrument every load and store in the program and do that. With some hardware support, for example, the debug registers, you can get. It's a little bit difficult to do that in Linux because it's all based on different processes, but you can make it finer grained so that if you're interested in one memory location, you can profile that.
So in the first, better. No, very bad. In the first graph show, was there one bar that was actually below the like was there one bar that was faster in the first one?
Oh, here on the left?
No, pretty.
It's probably due to measurement error.
Yeah.
Yeah, there's probably some error bars there that are missing.
Otherwise, I'll scream. The really cool work. Just out of curiosity, either of this thing just for WebAssembly, right?
Yes.
So how far would it be to apply your concept to existing just like have you investigated that?
Great question. So the overhead in terms of lines of code added to this baseline JIT was about 100. So it's effectively like you're running through the bytecodes. What bytecode is it? Oh, it's a probe. And then you do something special for probes. Literally none of the other instructions are impacted. That's a baseline compiler. An optimized compiler, you're going to have to like type it through many levels of IR. But that's one thing that we specifically talk about in the paper. We think this should be possible for other JITs to adopt.
Because I think that I can like kind of order things, but it seems like you have to like sequential order. And if you don't know what it's going to be, whatever order.
Right. So you would want to make that a kind of a barrier in the IR. So like you would treat it like a call to a host function, which can have unknown side effects. So the compiler won't reorder around it. No, only for the probes. The probes are, since they're nicely inserted into the code, they will effectively be an illegal opcode. So when the compiler parses the bytecode, it will know exactly where a probe is, and it should treat it effectively as like a call to an unknown function. Right. Excellent question. JIT does not support single stepping. It goes back to the interpreter for that. Yeah. That is a good question, and one of the viewers actually asked us about that, and the answer is yes. WebAssembly does have multi-threading. You have to put some locks around the metadata, so effectively around the probes, so that you make sure that you order those properly. But then, if you are like, obviously you implement your monitor in your own code, that has to support multi-threading too. So you probably have to do some synchronization in your data structures and your dynamic program analysis too.
With that, thank you, invite the speakers, AMB.
Good afternoon, everyone. I'm Yash from Alibaba Cloud. Today, I'm very glad to share with our work on performance debugging of microservices. And we use a technique called Shapley values to quantify the influence of all the possible root causes of a microservice system. Here is the outline of my talk. Before I start, I want to tell you a real story. Once upon a time, one of my colleagues just was on call, and just after he finished his dinner, he received an emergency phone call saying that, oh, our microservice is on fire. Almost all the system components are raising alarms. And as you can imagine, he must be very nervous at that time, maybe more nervous than how I am here. And he just didn't know how to deal with such a large number of alarms because it is almost impossible for him to check all the alarms, all the system components, and there are thousands of abnormal traces arriving on the fly. And at the end of the story, unfortunately, this failure lasted for several hours. And as a result, the performance of our software team is not good that year. And the bonus money at that year is also not very good. So as you can see, the performance degradation of microservice system can result in performance degradation of a software engineering team. So after that failure, we start to ask this question. Can we automatically quantify the influences of each possible root causes so that we are not that nervous when debugging the performance issues? Because if we can quantify the influence, we can figure out what is our priority to debug, right? And then we just develop and deploy our system with the input of the observability data. Observability data is very important thanks to the instrumentation. And for our microservice system, the observability data is standard that are log data, time series data, or matrix data, and distributed tracing data. And with such input, we output the probabilities for each possible system factors to be the root cause. And we deploy this system on thousands of machines, and it reduces 83.3% system failures over 1 year. So far so good. How do we achieve this? Let me explain our method to you. It simply has 3 passes. The first pass is called the forward pass. That is the counterfactual evaluation. And the second pass is called the backward pass that do the quantification of influence using the so-called Shapley values. It is not clear now. Don't worry, I will explain the details. So far so good. Some background. We do use some instrumentation. As I just told, we use a standard way that is called the open telemetry standard that is widely adopted in industry, I believe. And with this observability data, Let's continue on the previous example. I think this example is simple and maybe self-explanatory. And the main point of this example is that we observe there are two kinds of RPC calling relationships in microservices or other system. The first one is called the synchronous call, represented in the solid arrow. And the second one is called the asynchronous call, represented by the dashed arrow. As you can imagine, for the synchronous calls, the relationships between the parents operation and children relationship, they have a relationship called the additive relationship. Basically, the parents operations delay is the addition of all its children's delay. So far so good. And for the asynchronous calls, the parents delay is determined by the maximum of all the critical paths. Yes, remember this max plus calculus. It is our very useful physical model for the microservice system. And with such causal graph, the causal graph basically characterize the above functional relationships between all the system factors. And we can now answer the what if question. So what is the what if question? For example, we can answer the what if question. What if we increase the delay of the operation P1 from 2 seconds to 3 seconds on the end-to-end performance metric? And with our max plus calculus, we can answer, oh, the end-to-end performance metric will increase from 5 seconds to 6 seconds. And we define such a value function to be the change of the end-to-end performance metric when we change a subset of factors. Just imagine the tail is wagging the dog, where the tail is the subset of factors, abnormal factors, and the dog here is the end-to-end performance metric. And here is another example where we can have different sets to be abnormal and characterize the so-called value function. And with the value function in mind, we can do our backward path to calculate the so-called Shapley influence score. You may have the idea that the value function defined before just characterize what if we add something from to be abnormal. And we call you may have the idea that the marginal change of such value function just represent kind of the influence of this abnormal factor, right? This is very intuitive, but however, we might have multiple abnormal factors to be possibly to be the root causes. So we need to consider, and these kind of root cause factors may happen in arbitrary order. So here we consider all possible permutations and calculate such marginal change introduced by some abnormal factor and calculate the average to be its influence. Is that intuitive? If that is not intuitive, I would say this is just the definition of the so-called Shapley value. So what is the hell about the Shapley value? Shapley value is a Nobel Prize winning economic concept that helped Shapley to win the Nobel Economic Prize in 2012. And nowadays it is widely adopted in the machine learning community because they find it useful to explain the feature importance using the Shapley value. Just like explaining feature importance, as you can imagine, it can also be applied to explain the importance of some possible root cause. Right? That is an analogy. And Shapley value have many theoretical properties. For example, if we want our quantification to be interchangeable considering the interchangeable factors, and if we allow some dummy factors, and if we want to consider the causal relationships, then the quantification should be unique. That is to say, if you want to have some nice properties, then it is the only way for you to quantify the influence of the root causes. So far, if you only cares about the delay of the operations as the possible root causes, we are done, because we already know how to calculate their influences, and we can use such influences as a kind of probabilities for it to be the root cause. But in our real application, we have different kinds of possible root causes other than the delay of some operation. For example, we have the QPS burst. We have the resource limitation for the services and the machines. And we also have issues on the middleware, such as the database and the message queue. And we also have some problem related to new versions. How to consider these factors? It is also very simple. We just add some nodes into our causal graph and estimate the functional relationships between the added nodes and the already existing nodes. And after that, we can consider almost all the possible root causes in our real microservice system. Let me do a recap. We have two passes. The first one is the first pass is the forward pass that answers the what if question or do the counterfactual evaluation on how some abnormal factor will affect the end-to-end performance. And then we do the backward pass to calculate the Shapley influence score as probably the representing the probability for it to be a root cause. And in this paper, we focus on the physical models, which is in this quadrant. But if in your domain, you do not have such a lot of domain knowledge, but you have some high quality data, you can also build such counterfactual evaluation model in other quadrant. So I do think, okay. Okay. Here are some quick experimental results. We did our experiments on our production system. It is quite accurate. It is manually labeled as a ground truth, and it runs very fast, less than 10 seconds per trace. I am sure all of my content will be forgotten, but I hope the spirit can go through. One takeaway is that domain knowledge of the physical models are very helpful, which includes the max plus calculus and the queen model. And second is that Shapley value is an efficient and effective solution for inference quantification if you want to do some root cause analysis or performance debugging. That's all. Thank you. Welcome to any questions.
So it looks like you are doing instrumentation and capturing the information at the deployed system, right?
Yes, we just use some standard way to do the instrumentation, and we build on that.
But it might add some additional issues, some overhead. It might result that implemented code itself is responsible for performance degradation. Have you encountered any such issue or challenge?
Yeah, very good question. Just as the last speaker puts it, nowadays some instrumentation methods have no overhead. And for microservices, there is a standard way, the open tracing or the open telemetry standard. If you just adopt that, it will result in very low overhead, and we can just ignore it. Yeah. Sure.
It's like, there is a data transfer that happens between microservices using messaging queue, and that could also be, result of performance degradation. So how do you capture that in your causal graph?
Yes, the transmission time or networking time can also be traced in standard instrumentation or open telemetry standard. So you can just record it exactly to see how long it is for the networking transmission. If that turns out to be the main part of the delay or the high inference score, it will be considered as a root cause. Yeah. We just provide a way to locate or figure out what is the problem. We are the problem. And for debugging and solving the problem, we need some manual effort. Yeah. Thank you.
Next, Hugo.
The student helper was supposed to give me his laptop. Oh, yes, thank you. Just. All right, all good. So hi, I am Hugo Lefeuvre, and this is some of the work I did as part of my PhD at the University of Manchester. This is the result of a collaboration with Liege, UPB, and Unicraft.io. The new operating systems must support many applications to gather early performance numbers, showcase to investors, or gather an open source community. But manually porting applications does not scale past a few use cases. So what OS developers do in practice is leveraging a compatibility layer. And compatibility layers sit between the operating system and applications, offering them a familiar interface like POSIX. And they're very popular. Unfortunately, writing a compatibility layer is often viewed as a daunting task. For the Linux ABI, one must eventually implement hundreds of system calls. To write a compatibility layer, you would usually select an application to support, analyze which OS features it needs, and implement these. These steps feature a lot of hidden complexity. It is difficult to choose which application to support first, so developers use their gut feeling. Unfortunately, making the wrong choice will increase the time needed to support the first real-world use cases on the new OS. To determine which OS features to implement, OS developers would usually run the application and trace which system calls it executes. This naive dynamic analysis approach is popular since at that stage, developers just want to get something to run, however, it's error-prone. And this sort of trial and error approach also prevails when implementing OS features, as OS developers take shortcuts called stubbing and faking, which too are error-prone, and I will talk more about that in a few slides. So in the end, OS developers approach this compatibility problem in a very ad hoc fashion. Unfortunately, what we observe is that this approach results in a lot of unnecessary engineering and indeed makes the development of OS compatibility layers daunting. To address this problem, we propose Loupe, a systematic method to build OS compatibility layers. And the goal of Loupe is to optimize the traditional ad hoc approach I described earlier to support more applications faster. At a high level, Loupe is based on dynamic analysis. It simulates different degrees of application compatibility while observing application behavior to determine what OS features need to be implemented. Let's have a quick overview of Loupe. Typically, users would provide Loupe with an application and a test workload. Then Loupe starts the application and applies the workload. And while doing so, it uses Linux interposition facilities, so seccomp and ptrace, to hook into system calls and files. And it does so in order to simulate different degrees of compatibility and gather application behavior data. And this process is performed over multiple restarts of the application to cover the full OS API and ensure that results are reproducible. Finally, Loupe stores the resulting data in a shared database together with information necessary to reproduce. Users can then query this database to know which features to support for a set of applications and in what optimal order. Here, dynamic analysis is precisely suited because it matches the organic development process of an operating system. As support progresses, workloads can be extended to cover applications more deeply. For example, the first test could be pinging the application. A more complete one could be running a benchmark, and an even more thorough one would be the application test suite. And once all of this is supported, developers can leverage complete methods like static analysis to guarantee that there are no support gaps left. Unlike prior attempts to analyze the compatibility needs of applications, Loupe integrates two mainstream OS development practices, faking and stubbing, which I mentioned earlier. Stubbing is the practice of not implementing a feature and returning an error code. Faking is similar, except you return the success code. Both practices can be applied to any OS feature. They're very popular. To our experience, most OS projects do it at some point in their development. So during exploration, Loupe not only checks if a system call is used, but also if it can be faked or stubbed. And the ability to do that, again, is an advantage of dynamic analysis. Now, beyond the analysis, we need to guide users to choose which OS features and applications to support first. You may remember from a few slides earlier is this part where the user queries the database. And our approach to solve this problem is support plans. Support plans tell you which system call to support, when and how to support the next application as soon as possible. Here's a simplified example. For each operating system, steps are proposed listing system calls to implement, stub, or fake to support the next application. And Loupe does that in a greedy way by sorting applications after the compatibility needs, which it compares with what the OS already supports. To quantify the benefits of Loupe and its support plans, we evaluated versus the ad hoc process followed by the developers of an existing popular libOS called OSV, and versus a naive dynamic analysis baseline. And here are some results. Since both Loupe and OSV leverage faking and stubbing, they find that the same number of system calls are ultimately needed to support all applications. However, that is not the case of a naive dynamic analysis, which expectedly finds that more system calls must be implemented overall. The most interesting is when looking at the situation midway. So for half of the applications supported by OSV, where we can see that Loupe allows to support the same number of applications with 2 times less system calls. We applied Loupe to more than 100 applications and leveraged this data to perform a study on the development of OS compatibility layers. And I will go through some insight next, but there is more in the paper. First, we show that static analysis and naive dynamic analysis are quite pessimistic when used to guide the development of OS compatibility layers, as both significantly overestimate the minimal engineering effort needed to support a set of applications. Here's a comparison of static analysis, dynamic analysis, and Loupe for a subset of the dataset. For dynamic results, we show both data for a test suite workload and on the left and on the right for a benchmark. So looking at Loupe first, the number of system calls that must be implemented to support these meaningful workloads is quite low. On average, 20 system calls for benchmarks and 20 to 40 for test suites. We can clearly see how considering faking and stubbing in the analysis is a big gain versus a naive approach. In some cases, as much as 50% of the system calls do not have to be implemented here. Compared to dynamic analysis, static analysis is very conservative, reporting that 2 to 5 times more system calls must be implemented compared to Loupe. Although all would eventually need to be implemented in a production-ready system, this makes a big difference in the development stages. We discuss this in greater details in the paper. So all of this brings the question of why stubbing and faking is possible. Although those are extremely common practices, this has not been studied. We address this gap in the paper. We highlight 4 main application patterns which enable stubbing and faking. The first one is the application ignoring the failure of a system call. For example, Redis ignores the failure of the sysinfo system call as it is only used to feed debug logs. Another one is the application using alternate OS features. The glibc, for example, can use mmap when BRK fails. When the system call fails to return information or data to the application may also fall back to default known to be safe values. For example, Redis uses the getOurLimit system call to query the maximum number of files and uses a conservative limit when it fails. Finally, the application may also disable some of their own functionalities that use the faulty system call. And that is, for example, the case of the connect system call and the name service cache. Lastly, we also study when faking and stubbing is not okay and the potential pitfalls. In the general case, we find that stubbing and faking does not impact performance and resource usage. As for reliability, Loupe reproduces results over several runs, which is effective at weeding out stubbed or faked system calls that affect stability. Still, we show that there are important special cases and we study them. Here's a table presenting some of these special cases. I will go through two of them to illustrate, but we provide a much deeper discussion in the paper. A pretty clear case here is the write system called in Nginx, which when stubbed, results in log files not being written, which improves performance due to a reduction in the volume of I/O. Well, that may be functionally acceptable as long as the workload doesn't need logs. It may skew the comparison with a full-featured OS. Another case is faking futex, which heavily impacts performance and resource usage, both symptoms of the software not functioning correctly. In this case, very clearly the feature should not be faked as it impacts application behavior. For the purpose of the presentation, I chose system calls which are rather obvious, so write and futex, but many other cases are less of a clear cut. Overall, this calls for carefulness when stubbing and faking, and this motivates for tools like Loupe to more systematically evaluate the impact of these implementation shortcuts, which are very common in the field. To conclude, OS compatibility layers are essential for new OSs to thrive, but the current approach to develop them is inefficient and ad hoc. Loupe systematizes the development to support more applications faster. In this study, we applied Loupe to more than 100 applications to gather insights on OS compatibility layers. Overall, these insights provide a message of hope. Provided a methodical approach, good compatibility with existing software can be achieved without immense engineering. We have used and are using Loupe in the field to support the development of the Unicraft library operating system. And we're proud to say that all of this is open source. And having said that, I'm open for questions. Thank you.
Thank you for your talk. If you go back to the previous slide, I have one question about that.
Yeah.
So these problems, were they automatically detected by Loupe, or did you have to investigate the results manually?
So when you run Loupe on an application, you provide, together with the test workload, a definition of what it means that the application run correctly, so like a check. That's what Loupe checks by default. Loupe also ships with facilities to check the performance and the resource usage automatically. So yes, these were detected automatically. But if you want to check the performance and the resource usage, well, not the resource usage, but the performance, you need to provide a measurement of the performance, a way to measure it when you're giving the workload. So yes, this is done automatically. No.
And I was wondering, in terms of, I think this is kind of a follow-up question, which is, in terms of these like things that you want to kind of detect, are they very tied to the OS that you're trying to do, or how many of them are general across any OS if you wanted to build a new OS?
So, do you mean?
It's the pitfalls. So, you said that like there's a pitfall where I'm thinking of things like like maybe work or
Yeah.
some of these other things, like depending on what kind of OS I'm trying to build or I'm trying to build compatibility layer on top of, maybe some of these pitfalls show up that are just because of the OS I happen to be building compatibility layer for versus ones that are general across all of these.
Yeah, that's interesting. I think we're more considering the pitfalls from the perspective of the application, like as application properties, that depending on how the application is using the system call, faking it or stopping it may or may not result in bad things happening. I think I need to think a bit more to see it as an OS property. Yeah. Okay.
Really cool. I'm going to really comment centric. I think it's kind of really, I have a friend who's really web and they're kind of not going necessarily with the policy API, so I'm curious what general like this or that and uses the policy.
Yeah, indeed, it's quite POSIX centric. In fact, the study part of the paper is even the Linux ABI, so it's even more specific. But I think that you could generalize that to other APIs. I think that would work as well. Although here, yeah, I think it would work, but we're really talking about compatibility to an existing API. So we would take Linux, or sorry if I misunderstood your question. Or yeah. Thank you.
And this is the last session.
Are we good here? So hello, this is Guanyu from Shanghai Jiao University. I'm introducing Amanda, which is a unified instrumentation framework for deep neural networks. And this is the plan for my talk. I'm going from the motivation and our abstraction of the DNA instrumentation, and I will introduce our system design for the Amanda framework, and finally the evaluation. Okay, so I will introduce the background of how the challenges are current development of DNA tasks. And as we all know, the DNA models are used everywhere in our daily life. And there are many analysis and optimization tasks and focusing on the DNA models. For example, for analysis, we have adversarial attack, we have interpretability, and we also have profiling. And for optimization, we develop different algorithms like quantization, like distillation or pruning. And to develop this kind of DNA tasks, the common demand is shown here. For example, for pruning, this is the training and fine-tuning process of pruning algorithm. We have training and fine-tuning. And in the fine-tuning process, we have the DNA forward, we have DNA backward, and DNA update. And the user usually want to insert some code to perform the weight pruning to get the weight sparse, and they also want to prune the gradient after the DNA backward. And for profiling, suppose we have a training loop and there are many operators flowing in the process, and the user wants to gather the weight, the activation, and the gradient tensors from the execution process. And so the common demands of the DNA tasks are these two. They want to gather runtime information, which are the tensors, and they want to insert some user operation code to the DNA model. To implement this, we summarize some of the challenges. First one is the user has to deal with ad hoc entry interfaces. So we use PyTorch interface here as an example. For example, in the previously introduced two algorithms, for the weight pruning, the user may use the model.weight interface to access static weight. They may use optimizer.step to the gradient pruning. And for gathering information, they may use module.backward hook and for module.forward hook. So the development must handle with a lot of different ad hoc entry points. And the second challenge is there are many fragmented required tensors by different tasks. Here I summarize some of the popular analysis and optimization tasks and the required tensors by them. And one more thing here is the graph structure of the DN model are usually needed by some of the tasks, and it is not very easy to get for some dynamic scenarios. So the fragment tensors are another challenge. And finally, there are two different execution modes in the current machine learning library, for example, the PyTorch and the TensorFlow. So this brings another extra complexity dimension to the previous problems. For example, in the eager mode execution, all the operators are executed right after they are called. This is called the eager execution. And for the graph mode execution, the operators are first built to a computation graph, and this graph is called later, and also the backward graph. So together with the previous two challenges, the execution modes brings another dimension. So here is an abstract example. For example, we have different tasks: the profiling, the pruning algorithm A, the pruning algorithm B, and given different entry point tensors and frameworks we are dealing with, we may have to write different implementations. For example, for the profiling, we may need something like this. And for pruning algorithm A, we may need something like this. And also for pruning algorithm B, we may need another different implementation. So this is the example from real world. I collected from the GitHub community, and there are the SOTA pruning algorithms implemented by different developers. There are the static pruning project Tilewise, the dynamic pruning project Kofi, and the zero-shot pruning project Spots GPT, and they support different DNN models. We can see that they have to write network coupled mode for different networks, and this is really unextensible. So the problem is there a better way to develop those DNN tasks? And our solution is to borrow the the instrumentation idea to the DNN community. Okay, the DNN instrumentation is the program instrumentation idea is well known to all of us. It's just to instrument some extra code to an existing program, and in the DNN scenario, it's like we have a DNN model here, and we instrument some extra operators to the DNN model. This can be utilized as a unified interface. And this is an example for the binary instrumentation. At the left upper corner, we have the original code, and at the right upper corner, we have the instrumented code. So there are some instrumentation trampoline built with by the instrumentation framework to instrument the code to the original program. And in our abstraction, the ideal case is we want to apply the instrumented code to the DNN models. And the first step is we abstract the DNN model as the computation graph, which is organized as operators and connected by different tensors. And usually we have the before execution and after execution entry points. And so we can collect the instrumentation context, which is composed of different tensors and also the metadata for the operator. And we also can assign the instrumentation point for this operator. And together, this is connected to the instrumented code, and the user have only to deal with the instrumentation context and the instrumentation point instead of dealing with different DNN models one by one. And this is shipped as our Amanda framework. And this is a short comparison of the binary instrumentation and the DNN instrumentation. We have different entry point in binary scenario, for example, instruction and the function and program. In the DNN scenario, they are abstracted as operators, submodules, or the computation graph. And we also have the runtime informations. And these two terminology used in the instrumentation scenario are called the instrumentation points and the state representations. So here is an example. For example, we have a pruning tool, and it is applied to a ResNet. And first, we have the originally DNN execution code, which is very simple here. We just call the DNN model with a given input. And to apply an instrumentation tool, we have to use the Amanda.apply interface. So this one is decoupled from the original DNN model execution. And for the instrumentation tool, we have to register the operator instrumentation callback with the tool. And the inserted operator can be arbitrary, so I didn't give the detail here, but conceptually can do almost anything here. So by doing this with this flow, we can implement different instrumentation tools and apply them to different DNN models. And here are the main APIs we're providing. They're organized as the registration API and the instrumentation API, which we learned from previous instrumentation tools. And they are the registration API is a mechanism that decides where and what code is inserted. And for the instrumentation API, that is just the code to execute or insert it to the certain instrumentation points. And here is a detailed example of a pruning tool, which will also have the DN model execution. And for registering is the code we define where the callback is inserted. And for the analysis routine, we have to filter out the operators to insert the code and which kind of instrumentation routines and the target operator. And finally, we have the instrumentation routine, which are just the operators inserted to the DNN model for the execution process. And nextly, I will just briefly introduce our system because it is massive work. And we have a layered design, and there are 2 layers of APIs provided for the tool developers and the backend developers. And for the tool API, they are used for the users to develop different instrumentation tools. They're organized into different kind of APIs. And for the backend API, they are used to extend the Amanda framework to different backends, such as PyTorch or TensorFlow. And at the center, we have the Amanda core, which is the callback-centric management of the inserted callbacks to deliver all kind of cool stuff. And at the top, we have different instrumentation tools. One thing need to be stressed here is some of the built-in behavior of the framework is also delivered as instrumentation tools. So user can depend on some of our previously defined instrumentation tool before their tool to simplify their development process. Okay, so this is how we implement the Amanda framework. So we have different backend drivers dealing with the massive things and the ad hoc things of different backends, such as we have the graph mode drivers. Okay, sorry, here's typo. It should be graph mode drivers and eagle mode drivers, sorry. For graph mode drivers, we may have TensorFlow driver, and for graph eagle mode drivers, we may have the PyTorch drivers, and they are unified by a backend interface as the context and the actions, which is representation for the instrumentation context and the instrumentation callbacks. And they are management by the Amanda core, which will deal with some different things like how we manage different tools and how we map the callbacks to the right place and how we catch the callback for better performance. And this all together are delivered as the unified user level interface for the state representations and the instrumentation points. And finally are some evaluations. For the generality, we evaluate Amanda with some popular tasks. And you can see here that if you are using the machine learning library directly, they may only support a part of the networks and they are not, and you have to choose the correct interface. However, with Amanda, you can use the same interface for all these tasks. And for developer friendly, as Amanda can support different networks, so the user are no need to write multiple implementations for different networks. So the line of code needed, to implement a task are reduced dramatically. And for the latency overhead, I will just briefly, which can be achieved under 7% for both TensorFlow and the PyTorch. However, the TensorFlow is a little bit slower because the graph mode is harder to rewrite. And for memory overhead, is generally less than 5% because we are dealing with the memory management of the native machine learning library. So some of the tensors are kept for a longer time. So there are some memory overhead caused by Amanda. So that's it. Friday reached 12 minutes. So this is a summary. Thank you.
Like very impressive. It looks like you're doing so much with your instrumentation engine, but still you are able to have 7% over what is your secret sauce. So for this these numbers, do you include the work which needs to be done after the instrumentation, or it is just for instrumenting putting your books?
Yes, thank you. Because I really didn't introduce here in detail. So actually, the right figure, we just evaluate the breakdown of the overhead. So the blue part is the overhead brought by the framework, and the right part is for the instrumentation tool itself. So generally, for the framework, they can be limited under 10%. So, and as for how we achieve it, I didn't really make this clear because it's a really messy work. We have the cache management component in the Amanda core, which means we didn't keep all the instrumented code for all the operators all the time. After execution, we find some of the instrumentation points are null, so we just remove it and return to the native implementation, which will be faster. So,
Great work, great job.
thank you.
Once again, thank you everyone.